This lesson we're going to be talking about solving trigonometric equations. Now you can remember, a solution for any equation is any value that can be plugged in for the variable or variables that make the equation true. For an equation to be true, one side has to be equal to the other side. So if you were solving, say, x plus 1 equals 7. A solution to this equation is anything I can plug in for the variable that makes this true. True means equal. So obviously x would have to equal 6. If x was 6, 6 plus 1 gives me 7, 7 equals 7. So the solution to this equation is x equals 6. But that is extremely elementary, and we need to move much further than that. So what we're going to do is solve equations with trigonometric functions in it, but the concept is generally the same. I want to figure out what I can plug in for my variable or variables. In this case, we're only going to be looking at one variable equations that would make the equation true, make one side equal to the other. Now, some trigonometric equations are far easier to solve than others, just like any other equation, so we'll start with the easiest ones. Here's a couple of ones that deal with cosine. Cosine x equals 1. Cosine x equals -1/2. Cosine x equals 0. 3 different equations, but they all have the same form, which is going to be very, very important. They're all in the form of cosine x equals a number. If you can somehow get any trigonometric equation into a form similar to this, then we consider that to be very solvable. And that's not always going to be easy to do, but what this form is, and it's for cosine, but really this works for any trig function, is if I can get it into the form of trig function of a variable equals a number, then the method of solving it is actually very easy if you know your basic trigonometry. So let's look at this. There's a couple of ways to go about these. I'll show you probably one of the easier ways that is most common. Let's look at the first one. Cosine x equals 1. So I want to figure out what I can plug in for the variable that makes this a true statement. Essentially asking, cosine of what equals 1? And if you could tell me what you could take the cosine of to get 1, then you got your solution. The problem with a lot of these is there's not going to just be one solution. There might not just be one value that when I take the cosine of it, I get 1. There might be infinitely many values that when I take the cosine of it, I get 1. But at least try and find one of them. Now, how could you do this? Well, one way you could do this is to think about, say, your unit circle. Here's your unit circle. In the unit circle, cosine is equal to the x coordinate. So what angle around the unit circle has an x coordinate of 1? Well, that one right there. So if I took the cosine of 0, I would get 1. So then if I go back to my problem and I say, what would x have to be? Well, x could be 0. So that is a solution for the equation, but it's not the only solution. Another solution, if I go back to the unit circle, is anything coterminal to 0. So 2 pi. 2 pi and 0 are the same in that they end up in the same spot, and the cosine of each of those gives me the same answer of 1. So another solution would be that x could be 2 pi. Another solution is that x could be 4 pi. X could be 6 pi, and I could keep going like this. So what you're seeing here is that once I find one solution, and let's say my one solution is this angle right here, 0. Anything coterminal to that, so if I go around one rotation and I end up here, that would be 2 pi. That would also be a solution because that has the same x coordinate, 1. If I go around again 4 pi. Still get 1 again and again and again and again. I get all these answers. Now I can't just keep writing these answers down, so I have to have a more concrete way of doing this. Now there's a couple of things that you can do, but I say the most common way of writing this answer down would be this. I'm going to write my first answer down, which is 0. And then I need to say that essentially anything coterminal to that, which should be all these, is also going to be an answer. Well, how do I get something coterminal? Coterminal means I have to go a full rotation, so I have to add 2 pi. And then I add another 2 pi. And I add another 2 pi. Okay? So what I'm going to do is keep adding 2 pi, 2 pi, 2 pi. If I keep adding the same thing over and over again, that's essentially multiplying. So what I'm going to do is I'm going to say my first answer is 0 plus I'm going to add a 2 pi. If I'm going to add a 2 pi over and over again, I'm going to say 2 pi times k, where k is an integer. Integer meaning positive, negative, whole number, or 0. Because I could also rotate the opposite way. I can go clockwise or counterclockwise and still end up here. So I can really subtract 2 pi essentially too and keep getting the same answer. So this is the way we write our answer, which is something you're going to have to get used to. But what this means is when I put this on the end of something, and I say 0 plus 2 pi, or really any angle plus 2 pi k, is essentially I have this angle as an answer, and then by doing this, I'm saying anything coterminal to this is also an answer. So you'll get used to that pretty quick, but it might look weird at first. But this is a way of generating all these solutions. Okay? So again, not that difficult to come up with this answer if you know this. And that might be your hard part. But you should be familiar with the unit circle at this point. Right, let's do another one. Let's erase this. Alright, how about the next one? Cosine of x equals negative a half. The nice thing is this equation has the exact same form, so really we can use the same approach. What will we need to plug in for x so that when we take the cosine of it we get negative a half? So, boom, back to your unit circle. Cosine, x coordinate, negative a half. There, there. What are the angles we're looking at? 2 pi thirds, 4 pi thirds. So, if I go back to my problem, if x equaled 2 pi thirds or x equals 4 pi thirds, when I took the cosine of them, I'd get negative a half. Now here's an issue. These two, if I look at these two angles, if I just draw them, here's 2 pi thirds, here's 4 pi thirds. But these two angles are not coterminal to one another. And being that they're not coterminal to one another, I can't really get from one to the other. I can't get from here to here by adding some value and then get back to this one again by adding the exact same value. This angle is different than this angle. So what I have to do is essentially treat these as two independent solutions. And anything coterminal to the first one will also be a solution. Anything coterminal to the second one will also be a solution. So I can say my solution is x equals 2 pi thirds plus anything coterminal to it. My other solution is 4 pi thirds plus anything coterminal to it. And this is the solution to that equation. Okay, so there's another one down. Let's do the last one. So how about this one? Cosine of x equals 0. Again, has the exact same form. So what I want to say is what would x have to be so that I get 0? Back to the unit circle. X coordinate of 0, there and there. Two angles, 3 pi halves and pi halves. So the solution will be that x could be 3 pi halves or x could be pi halves. Either one, doesn't matter what order I put them in. You also could write it in degrees. I could say 270 degrees and 180 degrees. It really doesn't matter whether you give it to me in degrees or radians. But if you look at these two angles here, there's a way I can condense the answer. Yes, there are two answers, and no, they are not coterminal to one another in that they're not in the same location. Here's pi halves. Here would be 3 pi halves, right? That's this angle. That's this angle. I end up here. I end up here. But they are related to one another in another way, in that they're not a full rotation around the circle from one another, but they are a half a rotation around the circle from one another. So the idea is, rather than take this angle and add 2 pi to it and get back to here, then add 2 pi to it and get back to here again, and then do the same thing for this angle here, say, alright, I'm going to add 2 pi to it, I'll get back to here, add 2 pi to it, get back to here, and treat them as two independent angles. What I could do is say, let's start with this angle here. Okay, this is starting to get messy, but just bear with me. Start with this angle here, pi halves, and if I add half of a rotation, which is pi, I can come to here. Then add half of a rotation, which is pi, I can come back to here again, and then half a rotation, then half a rotation, then half a rotation. So rather than treat each one independently and add 2 pi to each of them, if I just start with one of them and I add pi to it, that'll get me the next one. Now if I add pi to it again, it'll get me the next one, then the next one, then the next one. If I do that over again, I'll say pi times k. Again, where k is an integer. Now you don't have to write where k is an integer all the time. It's going to just be understood that it is an integer. So this is my solution. So if you look back, there was 3 situations. One where we essentially got one solution, and each solution after that was coterminal to that one solution. We had another situation where we had 2 solutions and they weren't coterminal to one another or halfway around the circle for one another, so really we treated them like they were 2 independent solutions and we wanted anything coterminal to each. Then we have this situation where we get 2 solutions, they're not coterminal to one another, but they were halfway around the circle for one another, so I could take the same value and continually add it and keep going between the 2 solutions. In that case, I add this pi k. Now there are 2 other possibilities that could come up here, all still having the same form, but look a little bit different in terms of the way the answers are written. So let me give you those 2 first before we move on. Okay, 2 other possibilities. Starting off the same way, cosine of x equals, in this case I'm going to give you something like this, say 2/3. Well, here's the issue. If you try and do it the same way and say, alright, what does x have to be so that when I take the cosine of it I get 2/3? And you go to your unit circle and you say, alright, x coordinate, where's the x coordinate 2/3? None of them are 2/3. Alright, well, if none of them are 2/3, it doesn't mean this can't be done necessarily. It just means that I don't know that it's one of these special angles as I move around the unit circle. So if it's not one of the special angles as I move around the unit circle, the first thing you need to ask is, can it be done? Well, if I go back to this and say, can I even do this? Well, here's the thing. Think about what the domain and the range are for cosine. The range for cosine, which is the answers I would get out of a cosine, which is this, always has to be between -1 and 1. So as long as this number here is between -1 and 1, then this is doable. I just need to figure out what angle it is. Well, 2/3 is between -1 and 1, so it's within the range of cosine. So this is doable, but how do I come up with the answer? Well, one thing you're going to have to do is you're going to have to get x by itself, which means I have to get rid of this cosine. Inverse trigonometric functions can make that happen. If I took the arc cosine of x, I took the inverse cosine of the cosine. Doing this composition allows these to cancel and just gives me x. Now if I do that on one side, I have to do it on the other side as well. because whatever you do to one side of an equation, you do the exact same thing to the other side of the equation. Now look what I have. I have a solution for x. I know what x equals. Now it's not as nice as say x equals pi thirds or pi fourths or pi halves or whatever, but it is a solution for x. You could leave your answer this way, or if you really want to know what this angle is, because x represents an angle, you could plug this into your calculator and get an estimate for the answer. But other than that, there's no other way to do this because the answer is not a special angle like pi thirds, pi fourths, pi fifths, pi sixths. So this is the best you can do. Even though it started off the same way as all the rest, when this number is not a number you're used to seeing for cosine, which would be like 0, 1, -1, a half, square root of 3 over 2, square root of 2 over 2. If it's not a number you're used to seeing, first, is it in the range for cosine? Is it between -1 and 1? Can I do it? Yes. If so, use inverses. You could actually use inverses for all of these original ones too, but it's much easier to not have to. But this idea of inverses can be used to solve any of these trig equations. So that's my solution. Alright, one other possibility, and this is an easy one. Cosine x equals 5. Again, this is not an answer you're used to getting at a cosine. Also, this answer is not in the range for cosine, which means there's nothing I could ever take the cosine of that will ever give me 5. Anytime I take the cosine of any angle, I should get an answer between -1 and 1. So, in this case, if there's nothing I can ever use here for x that I could take the cosine of that give me 5, we would just say that there is no solution. So when this number is not between -1 and 1, this is your issue for cosine. So that's it. That's how you would solve a cosine equation. The key to all these is that I got it into cosine x equals a number was kind of where I started. And what that number was really the difference between what kind of answer I got, how I did the problem, and whether I even could get an answer at all. Now, some books, might do this, some teachers might do this, but another way to do these problems would be to kind of just look at this and say, there's 5 situations, memorize the 5 situations and use that to get your answer. I don't like using this very much, if at all. I like teaching sort of the method of how you come up with your answer than just instead of memorizing what the answer is. And the idea is, let's look at say like number 2. If I ever have this equation, this is the answer. And you could just simply memorize that if you wanted to, but I don't think anybody's going to, so I think it's kind of pointless, but I show it to you nonetheless. If this is the equation you have, this is the answer for that equation, etc., etc. If the thing that you're looking at is greater than 1 or less than 1, there's no solution. We just talked about that. And then this is the most common situation, is if you're taking the cosine of x and it's equal to something that is not 1, 0, or -1, but it is between -1 and 1, then this is how you write your answer. And again, this is nice to figure out how you write your answer, but I don't think anybody's going to memorize all this. So I'll show it to you. It's in the book, but I think the best way to learn these is not to just memorize this, but to learn how to solve the equations, which is what we did in the previous examples. Alright, so here's another one. But this one's for sine. The nice thing is that once you learn how to do it for one trig function, it's really the same process for all of them. So sine x equals -1/2. The idea is in the form of sine x equals a number, which is what we're kind of looking to go with. So you say, what would x have to be so that when I take the sine of it, I get -1/2? Alright, well, sine is the y coordinate. Y coordinate's -1/2. So we get, not that one. -1/2 would be here, or here. So here and here. This time, let me use the degree ones just so I show you how the degrees work. So 210 and 330. So that means x has to be 210 degrees, or x has to be 330 degrees. Now, one thing is that, look at these two angles, just like before. 210 330. They are not coterminal to one another. They are not halfway around the circle from one another. There's no way I can add a value between the two and then add it again and get back to where I started. You can't keep adding the same value and getting back and forth between this angle and this angle. And they're not coterminal. So we treat them like independent angles. Independent solutions. So I need to just say, okay, here's one solution plus anything coterminal. Coterminal in radians is 2 pi. In degrees, 360. So I just add 360 to each of them. 360 degrees. That's my solution. If I wanted to write it in radians, I would say, what would be 7 pi sixths and 11 pi sixths plus 2 pi k plus 2 pi k. Okay. And it all depends. Do you want to do radians or degrees? Sometimes it depends on the problem. Sometimes it depends on the teacher. I mean, I don't care. But some problems require one or the other. Alright. So sine basically works, if you see, the same way as cosine equations do. One thing to remember is when I have sine x equals a number, what number am I looking at? Well, that number has to be between -1 and 1, just like cosine. That's the range for sine. So if it's not, then there's no solution. So like something like this, there's no solution to that. If it's a number that you're not familiar with, like 4/7, it's still solvable as long as it's between -1 and 1, and we would use arc sine, or actually, sorry, I should write it like this: the arc sine of the sine of x equals the arc sine of 4/7. I'm sorry, I'm cramming this in here. These cancel, and I get x equals the arc sine of 4/7. Right, 4/7. So that would be the same way as before. Other than that, there's not really much difference here between the sine equations and the cosine equations in terms of the method. Just like with the cosine, you could memorize 5 different answers depending on what this number is, but largely I think the best way to do is say, if this number is between -1 and 1, you can solve it. You can solve it by looking at the unit circle and coming up with your answers. Are those answers coterminal? Are those answers halfway around the circle? Are those answers completely independent? And then if it's not between -1 and 1, then there's no solution. If you choose to memorize this and say, okay, sine of x equals 1, this is the solution, let me just memorize that. Sine of x equals 0, this is the solution, and so on. You could go ahead and do that. I don't suggest it, but like I said, this is the way you could do it. So I show it to you. If you choose to, feel free to memorize this table so you can get all your solutions. I think just using the method and having that method be the same for all types of equations, regardless of what function it is probably more beneficial to you. Okay, one more. This one now, tan. It doesn't matter what the function is. Treat them all the same way. This is tan x equals a number, right? So if it's in the form of trig function of x equals a number, they basically take the same form. What does x have to be so that I get that number? Tan is a little bit trickier though, because if you look at tan and you go to the unit circle, or any way you're comfortable doing trigonometry, you got to say the y coordinate divided by the x coordinate has to give me square root of 3. Sine and cosine are nice. You just say, okay, what's the y coordinate? That's the answer I'm looking for. What's the x coordinate? That's the answer I'm looking for. Tangent, you have to divide these and hopefully get the answer you're looking for. So square root of 3. Well, the only ones with square root of 3 in them are these two. So which way do I want to divide? Y over x in terms of the square root of 3 over 2 divided by 2, or the other way around is kind of the way you can narrow it down. Well, if I did the square root of 3 over 2 divided by 1 over 2, that's the square root of 3 over 2 times 2 over 1, because you flip and multiply. The 2's cancel, and I get square root of 3. So what angle had this as a y-coordinate and this as an x-coordinate? Well, if we go back, this one did. Pi thirds. The only one that would give you the same answer would be ones where I get positive square root of 3. Well, if I use this one, which has the same x and y coordinate, just the x is negative, I divide this by this, I actually get a negative answer, so that's not good. I want positive square root of 3. The only other one that's going to work out for would be this one. If I divide this y by this x, they're both negative, so I get a positive when I divide, and I'll get positive square root of 3. So here's my other answer. Now, one thing happens with these tangent ones all the time. And the thing that happens with these tangent ones all the time is we know that x could be pi over 3 or 4 pi over 3 when we just looked at it. But those two answers, and this is going to always happen with tangent, are directly halfway around the circle from one another. So I'll never have to really write these as two independent solutions. I can always write it as just the first solution plus pi k to get to the next solution, to get to the next, to the next, to the next. So I'll be able to write my solutions like this. So there's your tan. Now, as far as this number goes for tan, that number does not have to be between -1 and 1. This number has to be between negative infinity and positive infinity, which means tangent will never be a no solution. You're always going to be able to come up with a solution for x regardless of what this number is, because the range for tangent is this. And if this is the range, then that means I'm not limited to what kind of things tan can be equal to. Again, if you want to memorize something here for the solutions, you can say for tan x equals a, we can look at this particular solution here. We could do the inverse. We could just remember that this is the way we write our solution. But the one thing is that there will never be no solution. Again, I don't like this. I show it. I don't really want to teach it too much to you because I don't think anybody's going to use it. But it's there for you if you want. So now we need to start solving some more difficult equations. Now, the key to all of the equations we're going to solve is you want to get it into the form that's workable, in that you want it to be in the form of a trig function equals a number. So it's not going to always be that way. In this case, here's one. This is not in the form of cosine x equals a number. But through some very basic algebra techniques, we can make it that way. So I have 2 cosine x equals, or minus 1 equals 0. So if I want to get cosine x by itself, I'll add 1. So I get 2 cosine x equals 1. I'll divide by 2. So I get cosine x equals a half. And now it's in the form that I want, and I solve it the way we just got done discussing. What would x have to be so that when I take the cosine of it, I get a half? So you can always think back to here. X is the cosine is the x coordinate, so a half, here's my angle, here's my angle. So I say, alright, well, x would have to be pi thirds, or x would have to be 5 pi thirds. Those are independent solutions. If you think about where they fall, here and here, they are not coterminal to one another. They're not halfway around the circle from one another. I treat them as independent solutions, add 2 pi k to each, and that's the solution to the equation. But the key was to take this equation and put it in this form. Let's do another one. 2 sine x equals square root of 3. This is not in the form that we want, but it's very easy to put it in the form that we want. So what I'm going to do is I'm going to divide by 2, and I get sine x equals square root of 3 over 2. If we can take a function and write it in this form, sine of something equals a number, then it's solvable. What would x have to be? Well, we just got done looking at pi thirds, and the x coordinate was a half. Sine, we want to know what the y coordinate is. Well, guess what? That same angle, the y coordinate, square root of 3 over 2. We don't want the other positive y value, which would be over here, which would be negative a half, positive square root of 3 over 2. So what angle would that be? And that's your other answer, in this case 2 pi thirds. So x has to be pi thirds, x has to be 2 pi thirds. They are not coterminal to one another, so 2 pi k to each, and that will help us find all the solutions to this equation. This is the way we would write all the solutions. Here's another one, slightly different, but really we can solve this largely the same way. So if we look at this thing and say, okay, we want it to be trig function equals a number, we kind of have that, but instead of the inside being just x or just theta, it's 2 theta. So what are we going to do with this thing here? Well, actually we're not going to do much different than we've been doing. If I just said, let's let 2 theta equal x, right? Then what I get is sine of x equals square root of 2 over 2. And it's exactly the way we want. What would x have to be so that we get square root of 2 over 2? Well, x would have to be pi fourths, or x would have to be, say, or would the next one be 3 pi fourths? Alright, but this equation has a variable theta. And ultimately, if we want to find all the solutions, we want to find all the solutions for theta. What does theta equal? Well, if we know that 2 theta equals x, and x equals pi fourths, plus, really remember these things are independent solutions. Here's pi fourths, here's 3 pi fourths, so it'd be plus 2 pi k plus 2 pi k. So if 2 theta equals x and x equals pi fourths plus 2 pi k, then I can say theta equals x over 2, or this over 2, which tells me that theta equals pi over 8 plus pi k. If I divide this by 2, which really gives me pi eighths. If I divide this by 2, the 2's cancel and I get pi k. So there's my solution. That's just one of them. Remember, we had this other one, so that tells me that theta will also equal 3 pi eighths plus pi k. So here's the deal with these. If the thing inside here isn't just an x or just a theta, but 2 theta or 2x or 2 whatever, or 3 or 4, it's not that big a deal in that you would solve it the same way. Sine of what equals this. Come up with that answer, and then in the end you're just going to have to take these answers and divide them by whatever number is in there. And if you can do so, if this was, say, if this number right here, let me erase this so you can see it. If this number right here was a 5, so if it was the sine of 5 theta equals square root of 2 over 2, this would still be the same. The difference is here I'd be dividing by 5. So then this would be a different number, and obviously this would be different because they're dividing by 5. But that would be the only difference in how you solve it. The method's generally the same. Here's another one. Tan 3x equals square root of 3. Well, again, if I just say, let's let, I don't know, y equal 3x. Then I get tan of y equals square root of 3. We actually already did that, right? If you go back, we did this one. Let me see, where would it be? It would be here, not there, here. we did this, right? Remember, we did the tan of x equals square root of 3, or even if this is a y, it's the same thing. We came up with these two answers. I mean, the idea is with these two answers essentially yield this one answer. So if I use that and say, all right, well, y would have to be pi over 3 plus pi k. Then remember, 3x is my y, and y is pi over 3 plus pi k. So that means x, if I really want to figure out what x equals, because that's really what the question's asking, I'll divide by 3. So I get that x equals pi over 9 plus pi k over 3. And there's my solution. So I just really divide by that number that's here. So if your equation's not in the form of a trig function equals a number, like any of these, alright, don't fret. You can still solve them. Sometimes it's fairly easy to turn it into this form. And if it's not completely in this form, but it's the sign of something equals a number, then we can still do it, and then just figure out how we deal with that something by sort of replacing the thing inside with a very simple variable, and then working our way back away from that. Alright, now your equation is going to continue to get more and more complicated, but if you can always bring them back to trig function of something equals a number, we can still use the same technique. The trick is to bring them back to that. So here's one. Sine of 2x equals sine x. One skill that you're going to have to use quite often is factoring. When you factor to solve equations in algebra, your equation has to be set equal to 0. Something like x squared plus 2x plus 1 equals 0. This has to be set equal to 0 so that when I factor, I can set my factors equal to 0. It's something called the zero product property. So that's something that we're going to use quite often to get these into the form that we were comfortable with. Another issue here is this might come up in that if you look at this, the thing inside this one and the thing inside this trig function are different. And ultimately you would like them to be the same. It makes the equation much easier to solve. Well, if I have multiple trig functions like I do here, sine, even though it's the same function and the things inside are different, my first goal to solving this and to getting it into the form I want is to make these two the same. Now it's much easier to take this 2x and bring it down to an x than it is the other way around. So I'm going to say, how can I do that? Well, I can use identities. There are tons and tons of identities out there that we can choose from. In this case, this would be a double angle identity. And the double angle identity says that sine 2x is equal to 2 sine x cosine x. So this side of the equation is equal to this. That's through the double angle identity. Okay. The other side was just going to be sine, but now look at what's inside these functions. The same thing on all of them, which makes it much easier to solve. For the most part, the identities you'll probably use most often are the most basic ones that we've talked about, which would be the reciprocal, the quotient, the Pythagorean identities, but any identity technically could be used. Alright, now that we got that problem taken care of, the next problem we need to deal with is getting it into just trig function equals a number. That's where factoring is going to play. But in order to factor, you have to set it equal to 0. So I'm going to write this as 2 sine x cosine x minus sine x equals 0. So I need to bring this to the other side so that it's equal to 0, and I would subtract it. By doing that, I have something that can be factored. There's a sign here, there's a sign here, so I have sine x times 2 cosine x minus 1 equals 0. And then here's how factoring works. If you have things multiplied together equal to 0, one of them, either this one or this one, equals 0. Which is where we get to the point that we want, which is we can get to the point where it's just a single trig function equals a number. So this form is very solvable. This one I can put in the form of cosine x equals a half, add the 1, divide by 2. This one is very solvable. The total solution between them would be the solution to the original equation. Now there's something else to look here. The question said find all the solutions in the interval between 0 and 2 pi. Previous questions have just said find all the solutions. In this case, if we just want to find the solutions between 0 and 2 pi, we don't care about the coterminal solutions. We only want to generate the solutions that are in one rotation around the unit circle, 0 to 2 pi. Also, this interval is written in radians, and previously I said it doesn't matter whether you write your answer in radians or degrees, but if a problem is asking you something like this and the interval they're talking about is in radians, you should write your answer in radians. If this interval was in degrees, say 0 to 360 degrees, then the answer you would write would be in degrees. If it doesn't state that, if it just says find all the solutions and this isn't included, then it doesn't matter, but that's just something to look at. Okay. So, when would x be equal to 0? Or when would sine x be equal to 0? Sine x would be equal to 0 when x equals 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, but these are the only ones that are between 0 and 2 pi. When would cosine x equal to a half? Well, cosine would be equal to half when x equals pi 6, or, no, sorry, not pi 6, pi thirds, and 5 pi thirds. So those are solutions to that piece. So total, there are 5 solutions to this entire equation. 0, pi, 2 pi, pi thirds, 5 pi thirds, which means if I took any one of these, 0, and I plugged it in here for x, one side would be equal to the other side. If I plug pi thirds in here for x, it would make them equal. So they're all solutions. Okay? So this one was considerably more difficult than previous, and that's just the way things are going to go. Here's another one. Again, factoring is going to be a major way we do this. Sometimes we have to use identities first to factor, and sometimes we just go straight to factoring. This looks like something we consider to be quadratic. If I said, let's take cosine x out and replace it with, I don't know, y. What would happen? I would get 6y squared minus 7y plus 2 equals 0. If I said, solve this equation, how would you do it? Well, you would ask yourself what kind of equation it is. It's in a quadratic. How would I solve a quadratic? I could do factoring. I could do completing the square. I could do quadratic formula. So however I could solve this is really the way I could solve this. The only difference is I get a cosine, but it's not really in a different form than this is. So this one I would factor. Since it's equal to 0, I could do that. And I would get, what would I get? I would get 3y, y, I'm sorry, 3y, 2y, 2 and 1, negative and negative. That way I get 6y, no, that's not going to work yet. No. Yeah. 6y squared. 2, then the insides and the outsides give me negative 4y, negative 3y. Alright, so those factors work out. So if I do that same thing for the top one, I would get, remember, y and cosine are the same, so I get 3 cosine x minus 2 times 2 cosine x minus 1 equals 0. Now 2 things multiplied together equals 0 tells me 3 cosine x minus 2 equals 0. 2 cosine x minus 1 equals 0. Solve for cosine. I get 2/3. Solve for cosine. I get 1/2. Now it's cosine x equals a number. Let's start with this one. What would x have to be? So a half again. A half would be what, pi thirds or 5 pi thirds. Now look at the wording. Find all the solutions. So that's where we do have to do coterminal. So plus 2 pi k plus 2 pi k. Come over to this one. That's not a number you're familiar with the unit circle. So this is where we're going to have to say arc cosine of 2/3. And that's going to be my solution. And really, that's an angle. So I could leave it like that and that would be fine. But you'll say arc cosine of 2/3 plus 2 pi k. Because you want coterminal to whatever this angle is too. And this is just an angle. And you'd be done. So here's my solution as well as this. Here's another one. Looks very similar to the last one in that it kind of has a quadratic form to it, but remember, to solve with factoring it has to be equal to 0. So the first thing I'm going to do is I'm going to say 2 sine squared x plus sine x minus 1 equals 0. Now that it's equal to 0, I'm going to go ahead and try and factor it. So I have 2 sine x and sine x. And I got to go 1 and 1. And I want to get a positive, so let's say minus and plus. Okay, these two multiplied together give me 2 sine squared. These two multiplied together give me negative 1. The insides and the outsides multiplied together give me 2 sine x. And minus sine x gives me positive 1 sine x. Okay, let's erase this. So what does that tell me? Since it's equal to 0, and that's a key, if it's not, then this doesn't work. 2 sine x minus 1 equals 0. Sine x plus 1 equals 0. So sine x equals a half. Sine x equals negative 1. When would sine be equal to a half? When x equals, what would that be, pi sixth? Or when x equals 5 pi sixth. When would sine be equal to negative 1? When x equals 3 pi halves. Coterminal, because we want all the solutions, not in just 0 to 2 pi. So plus 2 pi k plus 2 pi k plus 2 pi k. So here are the solutions. Alright, so those are probably the most common equations that you would need to solve. The ones that kind of look like they're quadratic. I say those come up the most, or ones that just solve simply by factoring, maybe use an identity then factor. But I'd say these are probably the more common equations you would come across. Now they can get extremely difficult, but I'd say these would kind of be on the level that you're looking at right now. So here is one problem that is really difficult to solve. Again, most of them are going to look like the previous ones that you would ever come across to solve, at least at this level. But it's good to give you one hard one so you can kind of see how that would be done. There is some technique into this one that we haven't discussed yet, so this is a good example for that. But on a scale of say like 1 to 10 right now, 10 being the hardest, this one I would say is a 10. The other ones I would say at most are like 5s. Alright, so we look at this and say, alright, how are we going to solve this one? Well, think about it. One thing that needs to happen is the things inside the trig functions have to be the same. We have that, so that's good. If they weren't, this would be even harder. What else? We only want the solutions on the interval 0 to 360 degrees, so no coterminal, and our answer should be in degrees. We want to try and solve it by possibly factoring. Unfortunately, this thing, even if I set it equal to 0, really is no way to be factored. There's nothing common, it doesn't look quadratic, so factoring is not going to work. There's also no identity that I would immediately see I could use to solve this equation that would make it factorable, like we've seen in previous examples. So essentially, I have nothing that I can do to this. So if I'm looking to do something to it, I'm going to say, well, what can I do? And what I would say is, at a last resort, this is not something you try right away. This is something that you would try if you have no other options. You could square both sides of the equation. So if I did that, and I said, okay, tan 3y plus 1 squared equals the square root of 2 secant 3y squared. I can try and do this. Again, I wouldn't suggest it all the time, but you could do this. Now, why is this beneficial? Because what you're doing is introducing squares into the problem. And if you're introducing squares into the problem, you're introducing possibilities of using the Pythagorean identity. You're also introducing possibilities that you're now making it look more like a quadratic, which makes it maybe easier to factor. So this can be fairly useful. Now, you got to make sure you do it right. If I square the right hand side, these are multiplied together, so I can square this one and square this one. So if I square the square root, I get 2, and if I square secant, I get secant squared 3y. However, the left hand side, I cannot just square this and square this because of the addition. If I look at this thing, since there's addition here, I cannot do this and square both of these things. What I have to do is take this and multiply this whole thing by itself. In doing so, I would get tan squared 3y plus 2 tan 3y plus 1. And what I'm using is essentially my binomial formula for a square, which says if I have two things squared, I should use a squared plus 2ab plus b squared. Right? It's a plus b times a plus b. Multiply it all out, you get a squared plus ab plus b squared. ab plus ab gives you 2ab. Done. Alright. Now, that's what I applied. This thing here being my a, this here being my b. So if I do a squared, I square the first thing, which is that. If I do 2 times a times b, 2 times this is 2 tan 3y, times b is times 1, so I get 2 tan 3y, then plus b squared, which is plus 1 squared, which is 1. Alright. So that's where that came from. The biggest mistake I would see a student make would probably be that when they square the left-hand side, they square each of the terms individually, and you would get the wrong answer, because you can't do that. Alright, so now what? Well, this is still not very easy to work with. However, it's starting to look like a quadratic, but I got tans and I got secants. If I can make this all the same, then I'll do so. Well, since I have tan here and tan here, it's probably better to turn this into a tan as well, and since it's a secant squared, I can do that. Remember, tan squared theta plus 1 equals secant squared theta. So, I can say that tan squared 3y plus 2 tan 3y plus 1 equals 2 times tan squared 3y plus 1. Taking secant squared and turning it into tan squared plus 1. So what I get is tan squared 3y plus 2 tan 3y plus 1 equals 2 tan squared 3y plus 2. Now if I'm going to try and use factoring, because I'm thinking like this like it's a quadratic, I have to set it equals 0. So I'm going to bring everything over this way. So all those are going to be subtracted. So tan squared subtracted from 2 tan squared gives me tan squared 3y plus minus 2 tan 3y plus 1 equals 0. Alright, so now if I'm thinking of this as a quadratic, now I'm going to try and start factoring it. Well, if I'm going to try and start factoring this, it might be easier to take all these tans out and sort of think about how would I factor it and then go from there. So I need some more room here. So we have, let's rewrite this, tan squared 3y minus 2 tan 3y plus 1 equals 0. If I said, let's let tan 3y equal, I don't know, x, I end up with x squared minus 2x plus 1 equals 0. You should be able to factor that. What do you get? X minus 1 equals 0, or x minus 1 squared equals 0, right? Well, x is tan 3y, so how am I going to factor this? Tan 3y minus 1. Oh, this is 3, not cubed. Tan 3y minus 1 squared equals 0. Which is going to tell me that tan 3y minus 1 has to equal 0, or tan 3y has to equal 1. So now look at what I have. Tan of something equals a number. So I could just say, well, what would this have to be so that I get 1? What angle would go there? Remember, going back to the original problem, we only want the answer in degrees, and we only want it between 0 and 360. So what would it be? Well, 3y would have to equal pi fourths, but in degrees, 45 degrees, or 3y would have to equal, what would the other one be? The negative side. So 225 degrees. Remember, that's 3y. If I want to know what y equals, I divide by 3, so I get 15 degrees. Divide by 3, I get, what, 75 degrees? And there's your solutions. Again, this problem was not easy at all. Scale of 1 to 10 right now, that's a 10. You're not going to see it a lot, but it did bring forth this one possibility of maybe I'll have to square both sides of my equation. So in review, if we're solving a trig equation, know how to solve these basic ones. Sine x equals a number, cosine x equals a number, tan x equals a number. And if you can do those, then what you want to do is say, okay, if I have, say, sine x or sine of 3x equals a number, so it's some multiple of an angle, think of it just as if it was a single variable. How would you do it? And then divide by that number in the end. If it gets a little more complicated, you may have to start to use identities. You may have to use factoring. In factoring, make sure you use the zero product property. You set equal to 0. And I say this would be a large possibility of things you're going to come across. They're not always going to be this easy. And most of the time that'll take care of it. But if you're at a loss and none of this is going to work, possibly try and square each side of the equation so that you can use maybe the Pythagorean identities for squares and start to think of it like a quadratic.